Hello everyone, welcome to CIS125, Discrete Mathematics for Computing, or Non-Discrete Mathematics for Computing, if you want to have a little bit of a play on words. So good morning, evening, or afternoon, wherever you may be. This is Professor Bob. You know me by now, and I kind of know you guys as well. Thank you for checking in. You guys have been working really hard on your lab assignments, and you're finally starting to reach out to me. I really appreciate that. So continue to do so. Continue to work on this stuff. Some really insightful feedback coming from you folks. So I know you're getting into this, or at least you're digging into this. So I really appreciate it. So keep on keeping on. All right, this is what we're going to do today. We're going to talk about standard deviation. Now, standard deviation is really how spread out the numbers or the different numbers or the sample of a population or the specific observations of a population. Like, for example, you may have heard this analogy a little bit when you were in middle school math or maybe even high school math about, if you took the temperature of an oven, and maybe you didn't hear it, but and on one end of the oven, it was 450 degrees, and the other end of the oven, it was 0 degrees. So then you could say, well, let's use another number. Let's just say one end of the oven was 500 degrees, and the other end, like by the door, presumably, was 0 degrees. You could say that the average temperature of the oven is 250 degrees, right? Because you would just get the average or the mean temperature of the oven. Then you would look at another oven, and then you would measure the temperature of the oven, and you would say at one end it's 501 degrees, and the other end it would be maybe 498 degrees. Don't write these numbers down. I'm just trying to sell you in the general idea. Or 499 degrees. You could say the average temperature of that oven is 500 degrees. So those two ovens are different, aren't they? Again, I'm just selling you on the big picture. I'm not trying to trick you. Don't write all this stuff down. It's not a word problem. I'm just selling you on the big picture. Those two ovens are different, aren't they? One oven, it's very cold on one end of it, and it's very, very hot on the other end. And then you get the average, right? Okay, so what? Oven number 2 is hot pretty much throughout the whole oven, right? Although it is different. You observed different temperatures. You have different observations. And then you get the average temperature of the oven. So I guess what I'm trying to say is the average or the mean doesn't tell you the whole story, does it? When you are describing something. Now remember, when we use a mean is part of what we call descriptive math. It describes things. It takes what we observe and it helps us make sense of it. Now, some of the examples that you could go over for a mean are fairly obvious. You could look at, for example, the temperature, the high temperature for the month, like if we're currently in the month of February. And you would, presumably if it's the end of February, we could take the high temperature for the month and we can get the average, right? But let's just say that we were taking the average temperature on Mars, where the average temperature, the temperature of one day might be 0 degrees centigrade, and the next day it might be negative 425 degrees centigrade. So we would get an average for Mars. Now, if we took the average temperature of Mars and compared it to the average temperature of Earth, right, for February or whatever, those averages don't tell us the whole story, do they? Because one planet has a wild fluctuation in temperature, like Mars, right? The other planet, Earth, wherever you're at, Chicago, doesn't have as big of a fluctuation of temperature, does it? It fluctuates between 20 degrees, one day, 40 degrees the next, maybe 50 degrees, maybe 15 degrees, but we don't get a lot of variation in the temperature where we get, like if we, describe the fluctuation of temperatures on Mars. Now that's important because we have a mathematical equation for this, and this is called a standard deviation. The standard deviation tells us how spread out our numbers are. So basically, when we take observations, it tells us how spread out they are. So a higher standard deviation means that the numbers are more spread out than a smaller standard deviation. Now, I want to point out that a standard deviation is really a relative number. We compare it to other ones. So if you're just learning about standard deviations, just know that a standard deviation for a specific sample is really used to compare to standard deviations for other samples. So by itself, it's just a number, but we're going to use it later for some other mathematical modeling processes, such as we're going to look at some other laws called an empirical rule that talks about standard deviations. We're going to talk about some predictive math that we can look at standard deviations for a whole bunch of different things and compare them and make predictions based on what our standard deviations are. So just know for right now, a standard deviation is part of a puzzle that you're learning. And we're going to later take that piece of a puzzle and plug it into something else. Just like when you learned about a mean, you're finding out that a mean is kind of part of a puzzle too. If you look at the average for something or its mean, you kind of use it to compare to other things. Same thing with the standard deviation. Again, I'm trying to get you guys to exhale a little bit and not just, hyper focus on what I'm talking about and every single freaking number, write it down and trying to get the meaning of it and, and blah, blah, blah. Again, I'm trying to get you just to look at the big picture and to kind of learn how this all fits in. Because once you do that, and I've said this 1,000 times, everything else seems to fall together. So now that I described or gave you kind of a definition of a standard deviation and how it is, here's the formula for it. Now we got a new symbol here on the left. On the left-hand side of the equal sign, this is just a lowercase sigma. So lowercase sigma is the standard deviation. So the standard deviation is going to equal the square root of the sum of our samples minus our mean squared over the number of samples. Now say that 10 times fast, right? Let me go through that step by step. And you can always go back to the slides. So I'm just going to kind of continue with this. And if you want, you can always go back on your own. So let's look at this equation again. All right, and let's put a real-world example in here. Let's just say I measure, for my observations, the how long it takes me to drive to school every day, right? And I do it 8 times. So 8 times I drive to school, and I measure it. And just to keep things simple, it takes me 10 minutes, 12 minutes, next day 23 minutes, then 23 minutes, then 16 minutes, then 23 minutes, 21 minutes, and 16 minutes, right? Simple. Now, what we can do is we can look at this and do a few things with it. We're going to get the standard deviation, but first what I want you to do is I want you just to kind of settle in and just look what we're doing here. Okay, so we could look at this and, and it is what it is. These are just raw observations. I got a stopwatch and this is how long it takes me. They're just raw observations. Now, we only have 8 here, but in the world of statistics or descriptive math, if you're doing mathematical modeling like me, it could be 8 million or 800 million or 8 billion. This is why these equations are so important because they scale up very nice. We're only doing 8 here, but it could be a lot. More on that as we get a little bit more advanced. So anyway, the first thing that we do is we can look at this, and if we want to look at the standard deviation, or how spread out these numbers are, right? What we do is the first thing we do is we get the mean. Now the mean, I'm assuming you know how to do. So I'm not going to cover that here, but you know me. So the mean is 18. Now remember the mean is me, as you see here, or mu, depending on the accent. Me equals, or the standard deviation is 18. So if you look up, and I'm not going to use my mouse here, but if you look up in the equation, we already have here, we got me equals 18. So the first thing that we do to get the standard deviation is we need to get the mean. The mean is 18 minutes. So we could say, on average, it takes me 18 minutes to get to school. So what's the standard deviation of that, of all these different samples? If it takes me on an average of 18 minutes, what we can do is we can compute the standard deviation, which tells me how spread out they are. Am I right around 18? Am I spread out farther? What am I? Now, again, don't get standard deviation in your head too much yet about what it means, because we use it to compare to other things. It's just right now the standard deviation is just how spread out these numbers are around the average. So let's do that. So let's look at the second part here. Look at the numerator. We got sigma x sub I minus me, which is the mean, population mean, squared. This is what it looks like on the right-hand side. Now, the mean is 18, right? So you see 18 if you look on the left-hand side. So what we do is we take every observation, 10 minutes, 12 minutes, 23 minutes, 23 minutes, 16 minutes, 23 minutes, 21 minutes, and 16 minutes. We subtract the mean and we square it. Look at the equation. Now this is the point where you pause the video if this isn't apparent and you look at this and get it to soak in. Seriously. So you could do that if you like. I'm just going to continue, but I'll put a couple pauses in here to let you think about that. All right, but the numbers here on the right-hand side, again, I'm taking my samples, right, of how many minutes it takes me to get to school. I'm subtracting the mean, squaring it, right, and then summing it. Everything you see on the right-hand side where I get 192 is what you see in the numerator of this fraction, right? So we got 192 as the numerator. So now we need to get n. Now this is easy. N is the number of observations we have. So I'll give you an imaginary extra credit bonus point for what n is. N is equal to 8, right? Because we have 8 samples. Our population is 8. So that gives us to our third step, where basically now we have our fraction 192 over 8. Now again, this is where you scratch your head and you go, huh? And then you start looking at this and maybe start doing the math. Don't take notes. Do it. I mean, just go back, look at each of the samples and go through how I did this. This is where I need to change or maybe control the way you do this. Sounds like ominous, doesn't it? Controlling the way you do this. But it's I usually get that from when I teach live. I get people taking a lot of notes while I'm talking, and I don't know why. I'm like, why are you taking notes on this? You should just watch it, absorb it, and then when I'm done, go to the equation and kind of work it out. I mean, this isn't history class, right? I mean, it's not like you need to remember, dates and you got to write down what date, something happened, or it's not a woodworking class where you got to put down the steps in doing something, or a lecture on, fixing a carburetor if they're Star carburetors. This is math. In math, you really don't take notes. Sounds strange, doesn't it? But you really don't. You try to absorb the big idea. And then when someone says, hey, Bob, do you have any questions? You're like, you know what? Not right now. When we're done with the lecture, I'm going to look at the example and I'm going to dissect it, and then I'll come back with questions. That's basically how you absorb this stuff. So anyway, let's get back on track here. So the standard deviation is equal to the square root of 192 over 8. 192 is on your right. That's how I got it, right? It's all here. You could take a look at all the numbers. Nothing happens off the slides here. So we get the square root of 192 over 8. So what does that mean then? So step 4, we just basically get our standard deviation. Our standard deviation is 4.89 minutes. So this is where things are going to be anticlimactic, right? Because you're like, okay, so what? We have an average of what? Our average is 18 minutes with a standard deviation of 4.89 minutes. You're like, well, what does that mean? And that's a good question, because we really use the standard deviation just as a number to measure how spread out our numbers are. So we could say here in our word problem that Bob drove to school 8 times, and we measured each of the 8 times. And the average time it took Bob to get to school was 18 minutes with a standard deviation of 4.89 minutes. Now, I'm done here. This is how you get the standard deviation. But let me foreshadow something here. So this is what we use this for. Let's just say, okay, I have a neighbor. My neighbor's name is Tina. Now, Tina works the diner all day, right by Triton College. Now, she drives to Triton with me in a different car. And she lives in my building. I live in the city, and that's the city of Chicago, right by Wrigley Field, by the way. If you ever want to hook up with me at Wrigley Field during the summer, give me a shout out, as they'd say, and we'll go to a game. I live right by Wrigley Field, and I go to about 20 games a year. I've seen a lot of bad baseball in my lifetime. So let's just say Tina drives with me to school with a car, right? She's got a car, I got a car. And let's just say on her average, it takes her 18 minutes to get to work or to school, but her standard deviation is 10 minutes. See, that would tell me something. Again, I'm just kind of foreshadowing here. You're like, what would that mean if Tina and Bob have the same average time? On average, it takes Tina 18 minutes to get to school, and it takes Bob 18 minutes to get to school. But the standard deviation for Bob is 4.89 minutes, and maybe Tina's is 10 minutes. See, that tells us something because we use standard deviation to look at anomalies. Like, why is Tina's deviation bigger than Bob's, or why is Bob's standard deviation smaller than Tina's? It also helps us make predictions. Like, we could say, all right, well, if Tina takes 18 minutes to get to school, and Bob takes 18 minutes to get to school, and Tom takes 18 minutes to get to school, they both drive cars, they both live in the same building, and they both drive to the same place. They all have the same average time of 18 minutes, but all of their standard deviations are different. That could tell us different things. That could say things like maybe Tina takes a different route. Maybe Tina has a different car. Maybe Bob takes a different route. Well, that's going back to Tina's having a different route. But start thinking about that these numbers tell us things. They're just not numbers. And again, that's what I was mentioning in a prior video. That's what I don't like about math up to this point is you guys have been taught just to get numbers and not really remember the context or meaning of them. And that's why I'm trying to change that. Anyway, this is all I had for you today. This is how you get a standard deviation. So I went over the definition, at least my rambling definition of a standard deviation. I showed you an example of how to get one. And I started explaining the context of what it all means. So thank you for making it this far. I wish you health and happiness, and everyone, please have a very good rest of the day. Thank you.